Hi, in this video, we want to take a look at classical test theory, multiple sources of error. Okay, so what we're going to do, we're going to take some subtests that were from a collection of tests, and then we're going to do a generalizability study to understand the sources of variation in the data. Then we're going to use the output from the generalization studies to get more information about the tests themselves. And this will be we'll be using a decision studies for this. So the generalizability studies will compute how much each faucet accounts for variance in the data. And then we use the decision studies to get generalizability and dependability of these three subtests. Also, other information from decision studies will come out, such as standard errors of measurement and standard errors of estimation. Okay, so this example is modified from the Modern Psychometrics with R textbook. Here is the website where I got the code from. Here's the book. If you are a UCF student, you can download the book for free from the library using the Springer link. All right, so first thing I'm going to do, I'm going to load the data. So we're going to use the Modern Psychometrics with R package, and we're going to use the Lakes data set. All right, well, this is 3 subtests. So we're going to treat each subtest as its own and just see how things compare with each other. All right, so another model that I could have done, I could have kept this into one big model and could have used subtests as a faucet. I chose to break it up. And the reason for that is because of how things will play out later when we get into full model, reduced model. So we know that we have the subject's ID, we have the rater's ID, we have which item is being evaluated, we have the subject score, and then we know what part of the test it is. Okay, so from model exploration, I feel like each of the subtests should have a different model. Okay, so what I'm going to do, I'm going to break up the data. I'm going to use the split function to take the Lakes data frame, and I'm going to break it up into a list of 3 data sets based off of the subtest field. And then I'm going to go through and I'm going to remove empty levels of our categorical data. Okay. And so then after I'm done with this, I have a list of 3 data frames, and we can see that we have just under 6,000, just under 7,000, and almost 3,000 observation in each of the 3 data sets. Okay, so what I'm going to do now, I'm going to go ahead and do a G study, a generalizability study on these 3 data sets. And I'm going to do the full model. The full model will have the main effects, so 3 main effects and 3 two-way interactions. So we'll have person, we'll have rater, and we'll have item as our main effects. And then we'll take all the two-way interactions that we can possibly get off of these 3 main effects. All right. So here, my full formula is that score depends on, and this is a random effects model, depend on the person, the rater, the item, and then the interactions. And we can see that's our formula. Now, what I'm going to do, I'm going to go through for each of these data sets. I'm going to perform a G study from the G theory package, and I'm going to say that score depends on the full model. Okay, and you'll notice that right off the bat, I get some warning errors coming out. So here, it looks like we might have some singular aspects in our data set. That's definitely not good. And we can see that we have a warning about convergence. All right, so it's not like formally part of anything I've seen in statistics, but anytime I start having issues of like warning errors coming up, I take that as a flag I have bad model structure. So this is something that I would keep in the back of my mind. It's anytime that it takes a long time to converge, anytime that, so like here, for convergence, it's having issues with the maximum number of iterations getting within the tolerance. So that's a warning, it's a red flag. And then if I have issues with things with predictor variables being nearly singular, then I might be overfitting. I'm probably overfitting. Might be I just have very few data. And, you know, like when is it, you know, good, when is it bad? That's really a subjective call. And so we're going to be in the gray with a lot of this. All right, so I look at this, I look at the cognitive subtest, and I can see that I've got zero variance, and zero variance for an interaction term, a person ID, and a rater ID. And the interaction term with zero variance is, corresponds to the two main effects with zero variance. All right, so if I'm looking at how much variance is accounted for, zero variance accounted for means it's not doing anything in my model. So my opinion is that we should remove this. All right, now let's go ahead and look at effective. Effective has exactly the same three of rater ID, person ID, and then the interaction between the two as being something that we should remove. And now when we get to physical, we see that all of the components, including the interactions, are accounting for some variance. So I feel like for the physical subtest, we should leave this as is. All right, so at this point, when I was working through the code, I went ahead and I reduced the models. I did backwards elimination, and I concluded that the main effects models would be a good way to go. Now, here's main effects, and here's main effects. And I go ahead and I just, you know, rebuild the models. And then for physical, this is the same as the full effect, the full model. I could have just copied and pasted, done it actually a little bit faster. Looking back on it at this point, didn't think of it at the time, but the computation time isn't that long, so it's not an issue. But you'll notice I still have convergence issues. So if I was to proceed and I started feeling unsure about the model, then this would be additional evidence that I need to trim this back, need to make it a simpler model. Now, what would I do? I would probably remove, I would definitely remove an interaction term, and rater ID and item interaction is probably where I would remove first. After that, I would probably be looking at another, or I would more than likely I would be looking at another interaction term, actually definitely looking at another interaction term, and probably this one. But these percentages, these variances will shift after I remove terms from the model. So I don't know for certain. All right, so now let's go ahead and look at the output of the G study. Now here, this is for the reduced model. So here we can see that individual subjects and rater ID each count for 0.5%. That's not much. And let's see. Item is going to be definitely the big one for accounting for variance. And then we have the residuals, which is about half of the item, a little bit more than half variance accounted for. Now, when I look at effective, I see that I have zero variance from the individual. Now, I went ahead and kept it in there. I looked at that earlier and thought, maybe I should remove it. I decided to keep it. Why did I keep it? Well, I just feel that more than likely the individual person is going to be part of the situation, a part of what's going on. So I decided to keep it. But if I was to proceed to reducing the model, that would definitely be the first one I remove. And here we have the same as we had before. I'm yawning because I'm a little bit tired. All right, so now what I want to do, I want to use the G study, which gave me insight into the variance accounted for. I want to use that to do a decision study. So inside R, I'm going to take the G study output. I'm going to pass it to D study, and I'm going to get generalizability coefficient, the dependability coefficient, universe score variance, relative error variance, absolute error variance, relative standard error of measurements, absolute standard error of measurements, and then the relative and absolute standard of error estimation. And so for this part of the code, I'm just going through and I just, run it for each one of these. I do a for loop and I specify which study I'm going over. I specify the data set, and then I just say, what are the column names of the objects? What is the level of observation? For me, I take it to be the person ID, and this is consistent with the author's code. This is one of the reasons why I kept person ID in the effective portion, because for this project, the individual subject is the level of observation. So throwing that out means that the entire model would not be useful for the study for effective. And then here, the call names of the score is included. Let's see what we get. All right, so it gives us the variance components that we looked at before. It gives us the universal variance, generalizability, the relative error for the variance, gives us the standard error of measurement relative, gives us the standard of error estimation relative, dependability, the variance error absolute, the standard error of measurement absolute, standard error of estimation absolute. And it does that for each of the models. And on effective, we can see we get some weirdness on this. 0 generalizability, 0 variance universal, 0 standard error of estimation. Like there's something probably wrong with this model. So I would, if I was working on a real project with this, I would be like, hey, for the effective subtest, I think we should remove person ID from there. That's where I would start first. I would remove person ID. And if I like the results, I would stop. If that wasn't good enough, then I would consider removing rater ID. And by that, I'm probably going to be done. I think item would be kept in there no matter what. But you can see that this is very little variance accounted for in the rater ID. So I probably could lose it. This will probably increase after removing person ID though. All right, let's visualize what's going on. So here I'm just reshaping the data so that I can do a visualization using ggplot. And I'm sorting the terms in the model in a more sensible manner. All right, so here, this is the percent of variance accounted for. And so we can see that effective and cognitive is putting a lot into item, while physical is putting a lot into person ID. And then here we have very little elsewhere. And here's our residuals. And so we see the residuals are smaller than the others, the main ones. So probably pretty good. Now here is the variance accounted for, but not relative, the absolute aspect of it. And we see something similar to what we looked at a moment ago. And here's the N. We see that the residuals have a lot more than the others. Now, when I look at the decisions study output, we can see our dependability. We see that physical is by far the most dependable, and effective and cognitive are not dependable at all. We have similar results when it comes to generalizability. So a little bit for cognitive, but that is still pretty small. I mean, that's what, 0.3 or something? And then physical looks pretty good. Standard error of estimation, absolute and relative. I see that, it goes effective, cognitive, physical. Standard error of measurement, absolute. We see that now here we've got something going on with effective. And when I look at universal variance, effective has very little, cognitive has very little, physical has a good amount. All right, well, that's all I've got for you. Take care and goodbye.